Hello and welcome to my lab. You may have noticed that we've been playing around with streaming on our channel, and the idea behind that is that perhaps as we go forward we can stream our design and fabrication phases of these projects, and that obviously provides a bit more of an in-depth view and an easier way for us to make more consistent content. Obviously those videos aren't edited, they're just uploaded, so that's a lot easier from that perspective. But also it could allow for a little bit more interactivity between us and you guys. So you know, a lot of times when I design something, especially when I'm working with these videos for YouTube, I've got to design these things fast, and it doesn't give me much time to do the usual kind of in-depth analysis that you would do when you're trying to design something. So a lot of times when the video comes out, you know, someone will come in and comment, well, why didn't you do this? And in retrospect, it's like, well, a lot of those are, yeah, that is a very good idea, but I wish I had known that at the design phase. So maybe if we're streaming, that might give a good opportunity to have that, that interaction, you know, where it would actually make a difference. So maybe it's a terrible idea to try to design stuff in front of the internet, but it might be cool too. So we'll be experimenting with this, and I mean, obviously if it doesn't work out, we'll just drop it and go back to what we were doing. But it's interesting to try these things. That's what these tests are for. I think that's all there really is to say about that. Before we get into highlighting what's been happening on this project, I think I should probably give an overview for those who haven't seen any of the live stream stuff. So this project here is going to be a test setup for making clear ice. Now, this isn't, it's not to be confused with a device that just makes clear ice. I want to know what I need to do to make clear ice. So this is more of a scientific setup, which is why, you know, there's so much going on here that you wouldn't necessarily build into a device. I want to be able to, this is going to be a touch screen. It doesn't show up on the picture very well, but there's going to be a whole control system where I can set up all kinds of tests. The base concept of this is that there's an aluminum block in here, and that aluminum block is going to be cooled with what are called thermoelectric coolers, or Peltier devices, if you're more familiar with that term. And these are essentially electronic heat pumps. If I pass a current through them, it's a little plate. I have them somewhere around here, hold on. Ah yes, here's one. Let me just open one of these. I think it's pretty important for you to see this, so I'll just go ahead and show you. So it's got two sides here, two ceramic sides, and there's some electronics in the center stuff going on here. Technically those are transistors, but it doesn't really matter, or diodes, or something. I'm actually forgetting, but it doesn't matter. The fact is that if you pass a current through this thing, it's going to make one side hot and the other side cold. Now, if you take like a CPU cooler or something and you make the hot side cool, or you pull the heat away from the hot side, the cold side gets really cold. And so it's an electronic heat pump, essentially. Now, you can't see it in this picture, but we'll get to showing this. There are some at the bottom, and there's a water cooling system that's going to pull the heat away from it. Now, that will allow this block to get cold enough to freeze water, and so all I have to do is pour water in there and turn it on, and it's going to make ice. But that won't make clear ice, and I want clear ice. So I've also added the ability, now there's a vibration motor right here, and that's going to be able to shake this whole thing as it's freezing, and maybe that'll make clear ice. And also I've got the ability to apply a vacuum to this chamber, because that's kind of my idea. If you lower the pressure above that water, you're theoretically going to be pulling the high energy particles out of the system, and all of the air, nitrogen, oxygen, all that stuff is going to be more volatile, so that's going to get pulled out of the water if you reduce the pressure in that chamber. So I don't know if that's actually going to work or not, which is what this test is for. And then I can do combinations of all of these things. If I actually need to heat it, I can run the Peltier devices backwards, and then you just flip which side's hot and cold, so I can actually heat this water and then put it under a vacuum and stuff like that. And we'll get to that in the next video as we actually do the tests and figure out what is and is not important to making clear ice. And one thing that's nice about being able to run those Peltier devices backwards is that once you've finished making your ice, I've got this set up here so that this whole thing inverts, goes upside down, so that you can turn those Peltier devices to heating with this upside down, and maybe, hopefully, the ice cubes will just fall out as the boundary layer there gets melted. So instead of being frozen to that aluminum, it'll have a little bit of melted space, and maybe it'll fall out, I'm hoping. So then you could just have a plate down here and you'd get your ice there. So as usual in my devices, there's a lot of assumptions built into this thing, and hopefully it will teach us a lot in the process of building it and also using it. Of course, that's my primary purpose for building anything, is just so that I can make a bunch of assumptions and learn where my assumptions were incorrect. That's what makes it fun for me. Then as a consolation prize, we're also going to get clear ice, because people go through a lot of effort to make clear ice, putting it in a cooler in their freezer, and then they end up with a big chunk of clear ice with a big water bubble on the bottom, and they have to take a hacksaw and try to cut it into cubes and stuff. You can look up videos on that if you want to. But I don't want to do that. I'm a busy man, and ain't nobody got time for that. So, of course, I spent several weeks designing and building a system to save me time. So let's take an adventure on how that happened. Follow me. So the first thing we did was mill out this aluminum block that's going to actually freeze the ice. I'm only going to show you the interesting stuff here. First thing I did was bore out this hole that needs to be pretty accurate to press the bearings into. You'll see that later with the bearings in it. And then here we're slotting out the bottom area where the thermal electric coolers and some other stuff are going to go. This is going to have the water block in it as well. This kind of work gets really tedious really quickly on a manual mill, and I'm cutting out most of what we had to do in these 2 streams it took to make this block. So you're welcome. On the pockets for the ice cubes, I removed most of the material first using a drill, as you can see here. And that makes it a lot easier, especially when you're on a manual mill. If I were on a CNC machine, I probably wouldn't have done it that way. But once that's done, you can just plunge down with an end mill and clean it up. So here you can see also the bearings that are press fit in there. Those are going to stay in there because the hole I cut is about 1/1000th smaller than the actual bearing. Moving on to the frame, I can cut everything really accurately on the bandsaw and then put any holes I need into that with the mill. And that prepares everything to hopefully be TIG welded together without any filler metal. And I don't get to TIG weld much, so this is a pretty fun thing for me to play with. A lot of times while I'm MIG welding, I will not clamp things down and give myself the personal challenge of using how I weld and where I weld to compensate for any distortion that I might get. I tried to do the same thing here with TIG welding, and a combination of not having the best skills and also TIG welding being a little bit different. I ended up with a bent frame here, but also thankfully I designed it so that the frame being bent didn't matter too much. Now we can move on to test fitting. I printed this electronics enclosure in 2 pieces because it was too big to fit in the printer. I'm going to use this drive to fit them together, and then I can actually weld them using a 3D printing pen thing. I just started using this process, and it actually works pretty similar to MIG welding. I can tack things down just like you usually would, and then fill it in. If you apply light pressure and keep that puddle a little bit in front of you, it seems to adhere really well. I mean, just like it would in the printer. So with this process, you can theoretically print arbitrarily large objects and then just weld the pieces together. With that done, I can start testing the fit of the frame. Here I'm starting with the radiator for the cooling system, and then I can test the electronics enclosure. And this is one of the only pieces I actually had to modify because the frame was bent. So I had to slot out some of these holes in the top just to get the screws in place. Then I moved on to testing the fit of the pump and reservoir for the water cooling system. These are going to be hard to see later, so try to remember where they are. And then here I'm just testing to make sure the rod can fit through the clearance holes that I made. With all the fitment tested, then it comes time to powder coat the frame. And this is always one of my favorite parts of the process. It's just really fun to see this stuff go on. While preheating the oven, I bothered to check inside and realized I had accidentally made some art. So there you go, bonus project, very nice. When moving things from the coating area to the oven, I find that the wire wrap method that I use is a little bit of a pain to deal with. I think in the future I might get some hook that I can wire wrap around first so I can just hook it on. You'll see it's kind of annoying to try to wrap this around in the middle of the hot oven. It doesn't quite look it, but it's uncomfortably hot in there. Still, when I get it in there and close the door, all I have to do is wait for the cycle to complete, and then we have our part. And I just love the finish and durability of powder coat. It makes everything look really nice and professional when you're done. Now it's time to work on the business end of this thing. Here's the water block. I went ahead and lapped it down a little bit smoother just to help a little bit with the conductivity. This is going to be able to fit 4 of my little Peltier devices, these thermoelectric coolers. And I'm just going to build this up as a big sandwich that'll get clamped onto the block later. So I'll start with grease and then spread that out nice and even. Now this is a bit heavy, but it'll get squirted out as I clamp down on it. And I just want to make sure that it's evenly coated. So I can just place the whole assembly on the block here, and then I've got this force spreading plate so that I can clamp down on it with this one screw and, of course, hopefully not break the water cooler. And this part here just bridges the gap between these two with these screws. And this is a 3D printed part with an SLA printer, and these parts are pretty strong. I'm clamping down on this thing pretty hard. And then I've got a lock nut here, so it should not back off. Now I can work on the shroud/vacuum chamber part here. This thing's going to have an O-ring seal on either side to provide a vacuum, and it's also going to cover up the insulation on the outside. Now, I don't trust FDM 3D printed parts to hold a vacuum, so I'm going to use some of my UV Cure resin from the SLA printer to kind of seal it up. And, I can just paint it on and then cure it in my little curing box here. There's another nice use of that resin. I actually left this hole as a through hole because this NPT tap that I'm running into it actually kind of wants to go through it. And then once it's finished, I can just go ahead and put a little tape on the back here and then fill it in with resin and then cure it. And then I have a hole that, has a bottom to it. And this hole is going to be for carrying the vacuum into the chamber. There's actually a little hidden hole that goes all the way through to the chamber. Then I'll take a quick break from that block to work on the frame. This part here is actually going to latch the shaft in one of 2 positions so that you have an up position and a down position. You'll see in a minute here. I'm just getting this spring in place, and then I just use a bolt as the shaft. And there you go, springy latch. Now I need to put the pillow blocks on and the shaft in before you can see what that's actually latching. And here you can see I've got a handle that is also going to interact with that latch. And there is surprisingly tight tolerances here for a 3D printer. Once again, I'm really enjoying the SLA printing. Going back to the cooler block, I need to coat this thing in insulation. I'm just going to use this green insulation, cut it into pieces, glue it on, and then cut it to size. It's a little bit of a pain, but it works. Now you can see here I tried some E6000 and it just ate through the foam, so I suggest some spray adhesive if you're working with foam. Here it is after I glued all the pieces on and then trimmed it down to about 1 inch thickness. And this just lets me fit it into that shroud we were working on earlier. Now there's still some holes that I need to open up for the shaft to go through. So I'm just going to use a hole saw and just crunch it through. inelegant, but it actually works pretty well. Then I just have to pick out the carnage with some tweezers. Got to be careful with these shafts. If you push it through a little too hard in one of these bearings, you can knock out one of those tiny balls. And good lord, those are hard to find. But it doesn't look like we have any problems here. Nice, easy motion. Very rigid. Now for the vibration motor mount. I put a bunch of screws in this thing because I do not want it to rattle loose. And I mean, this motor is enormous, and it's actually very difficult to hold on to, and your hand goes numb if you try to hold on to it. So I really didn't want to slouch on that part. But yeah, the motor just slots in here, and I've got some room for both the ventilation and the wires going around here. And then you just get one screw for clamping down on it. Now, these are the rails that the whole block is going to ride on. And so these, I got them really close on the mill, just a little bit undersized so that I could tap the shafts in and have them really well retained, at least hopefully. Then I'm going to be putting springs on either side of the block so that it can rattle back and forth between the two springs and hopefully not just shake the entire frame. So I'm going to have to put the block on the rails and then a couple more springs, and then I can tap on the other side. And now you can see the spring action here. Now this is only going to work at certain frequencies, so we'll have to play with that. Now it's time for the rather involved process of getting the cooler block into place. I can slide one side in just like this, and that's pretty easy. But the other side's a little bit more involved, and you'll see what I have to do here. First, I just get the pillow block into place, and then I use the clearance hole in the frame to sort of hide the shaft, get it out of the way. Then I can bring the cooler block back up and then tap the shaft back into the bracket there. Then I'll just use a set screw to keep it all in place. After that, we get to put the handle back on and then test the whole thing. With that all working, we're on the home stretch. So now I'm just going to start routing the vacuum and water tubing. The vacuum is just going to route straight to the chambers, so that's pretty easy. I just need to make sure that there's enough hose to go all the way around to the down position. The routing for the water cooling system is a little bit more complicated. This here is the reservoir, and the bottom is going to go straight to the input of the circulation pump. And this is going to get pretty tight in here. Then the output of the circulation pump is going to go straight into the water block. After this point, everything started to get too tight to record. So here's what it looked like when it was done. The water block then just went to the radiator, and then the radiator went back to the reservoir. And here I'm just filling up the reservoir. And of course, this is still too tight to record. But at least it works. Okay, so I went ahead and did the electronics wiring and testing and stuff because that gets super tedious and I just don't know how to make that look interesting at all. So I'll just go ahead and explain what we have now that I already did it. We've got our touchscreen here. This is going to have, all our controls on it to change what's going on in the process. That connects directly to our logic controller, our PLC here. And really all I'm doing in the enclosure is changing a couple of different voltages because I need 5 volts for some things. And then I'm going to be running signals from the PLC into what are called H-bridge motor drivers, because most of everything we have to control on here is either a motor or just needs a constant voltage or something. So I have this wired up so that as soon as system power is applied, the fans on the radiator as well as the circulation pump back here that you can't see turn on. So they're just going to always be on if the system's on at all. And that's just both easier to wire and also a bit safer because it's just always going to be cooling the Peltier devices in here. So I don't want to end up in a situation where I've got the heat pumps on, but they're not being cooled because they can just come up to temperature and destroy themselves very quickly. And then I've got, of course, our vacuum pump in here, which is going to be powered off of a, it's kind of back in here. I don't think you're going to be able to see that very well. This thing's going to be packed when I'm done. But I've got that thing wired up to an H-bridge. The vibration motor here is wired up to an H-bridge. And those are going to be powered off of one power supply right here in the middle. And then I've got also another H-bridge is going to drive the Peltier devices. Now I've got 2 in series, 2 in parallel, and it's actually a dual H-bridge. This is all nerd stuff for people that actually care about this, but I'm just running one signal from the PLC into both inputs on the H-bridge, and then that's just going to drive all my Peltier devices off of one power supply back here. So this power supply gives me 5 amps maximum, and I'm splitting that between 2 Peltier devices, so that gives me 2.5 amps. And that's really, it's the amperage that gives us the effect. So they're rated for 10 amps, which means we're running this thing essentially at 25% power. And even though we're only running it at 25% power, that's actually enough to freeze the ice. So if I want more power later, I can get a bigger power supply, but I think this is going to be quite sufficient for now. Oh, also another thing I did off camera was the gasket on top didn't print properly because this side was the bottom in the 3D printing process, and it just didn't work out. So what I did was I just printed another one of these the right way up, and then I just welded it on using that same process we talked about earlier, and that works really well. It holds a vacuum, so that's just perfect. And then I've just got, you know, some plexiglass up here so we can see through it. And that just goes onto that gasket with a little bit of vacuum grease. It has way too much vacuum grease on it right now, but I'll clean that off. So I'll go ahead and turn the system power on, and then we can start seeing what it does. So you might be able to hear, that's the circulation pump and these fans turn on. And it is all, yep, it's all circulating just fine. So right now, I'm gonna make a better program for this, but right now I just have a couple of buttons on here just to test whether I can turn everything on and off properly. So I can turn on the vacuum pump, but it needs power from the power supply. There we go, you can probably hear that. That's not interesting until we get into things, but the more interesting part is the vibration motor here. So I don't know if you'll actually be able to see this on camera, but it is vibrating. And of course, like I said earlier, this dampening system here is going to be dependent on what frequency I run the motor at. So I'm gonna actually have to play around with what frequencies I give it. That's actually working a little better. So I can actually kind of put my hand on here and feel how much vibration there is, and put my hand on the frame and feel how much vibration there is there as a quick way of just testing some of the frequencies. I don't think the frequency is going to matter too much for just getting rid of bubbles. I just want to make sure the maximum amount of energy is going into this and not just dissipating through moving the frame around. And then of course I've got a button to test the Peltier devices, and that's entirely uninteresting until we really get into it. But I have run this, and it does make ice. I've made some, but we'll take a look at that in the next video. Of course, it was not clear yet because I specifically didn't apply any vacuum or any vibration because we're not to that point yet. So the next video is going to be all about us actually testing the process of making clear ice with this thing. So we'll run all kinds of tests with just the vacuum, just the vibration. I've got a couple of different sequences I want to try, and we'll see what kind of results we can get. So I'm gonna, between now and the next video, there's a couple of things I'll clean up. I'll go ahead and clean up this wiring and get that all closed up, but I don't think that's very interesting for you guys to see, so I'll just do that house cleaning there. So I think that's everything. So Thank you for watching, and we'll see you next time.